My name's Eric Krogenberg.
And I'm Tad Cook.
We began looking at compost as a potential source of heat for year-round greenhouse production for small-scale farms throughout Vermont.
We looked at basically taking a system that was designed in France and applying it to the average sort of small, diversified Vermont farm. And so that was taking woody biomass in combination with manure feedstock from small dairy operation and using them in tandem to create piles that would yield both heat and potentially gases that could be used to enrich greenhouse production. We went into the first semester of our sophomore year sort of looking at how we could expand that system to be relevant to farms across the state and what scale was necessary to really have an impact. And so we worked with some students, a PhD student in the GUND, and some other sort of graduate students that were working on this already to figure out how we could basically leverage what was available at UVM to make an impact on this field of study and to provide a resource for farmers. That sort of culminated in us applying for a Clean Energy Fund project to study how you could take an existing manure source on dairy farms and without changing manure handling practices immensely yield heat and enrichment gases, so CO2 and nitrogen gas for greenhouse production year-round. And that's the project we've been working on for the last 2.5 years.
Our actual major is called Ecological Food and Energy Systems. So it's looking at basically exactly what our goals were in this compost project, the intersection of food, waste, and energy.
Compost research is a pretty small field in this particular area. There's really a lot of going on in large-scale compost, but there isn't a lot in this specific area. So Bruce is someone that we connected with through UVM faculty and staff that had worked with him in the past, and he's been involved and been a visionary in this field for a long time. And he's really one of the only people that's done this kind of work throughout the country, and he happens to be down in Boston, so he's relatively local. And then Jason McKeon-Sanders, who's an engineering grad student here at UVM, but also the consultant on the project, and he oversaw the actual construction of the system. That was another example, sort of the small network of Vermont and how he's here at UVM, but he's also doing this kind of work independently. So it was nice to be able to bring in someone that's sort of a national expert that happened to be down in Boston, but also someone that's local that's doing the kind of work and that's also part of the UVM community. So compost heat is the idea that existing feedstock, biomass, natural material, as it decomposes, naturally releases heat. And the idea behind this system that we're working on and sort of the broader field of compost heat is that either through water or through air transfer, you can capture that heat and use it for another source simultaneously with the existing process of composting. On farms, anything from a dairy farm to a more diversified farm, you're going to have existing feedstock, manure, wood chips, hay, bedding, that's decomposing. And right now, manure management is really focused on how do you contain that process and produce a quality end result. And so our system looks at how do you integrate something that captures heat with existing compost or manure handling systems, which is sort of the day-to-day grind of a farmer taking the manure and using it and processing and then returning it to the field. In our system here, we're looking at how to take a stationary pile of compost and draw air through it and use that warm air and the gases that are a part of it to benefit greenhouse production. It's heat and it's also nutrient enrichment.
So the compost feedstock is a combination of manure and wood chip bedding collected from the Miller Research Farm over on Spire Street. In composting, you're looking at a C to N ratio, so carbon to nitrogen. If your nitrogen is too low, the compost doesn't heat up enough. And if it's too high, it heats up too quickly and for too short amount of time. Our system, it's about 20 to 1 carbon to nitrogen. Classic is kind of the standard is 30 to 1. Since we have a higher proportion of manure, our nitrogen's a little bit higher, but in that case, it kind of works to our advantage. So we have a slightly smaller duration of time that the compost is in the bay, but while it's there, it's at a slightly higher than normal temperature. So our system is looking at how you cycle in that compost at that correct ratio to take advantage of peak heat and gas production. A static pile where we're aerating it, the actual composition is much more important. So if you have a really dense or really wet pile, you can't pull the air through it, and then there's kind of segmented parts of the feedstock that don't compost. So for this, we're using some additional wood chips of a kind of a larger particle size, which allow air to be pulled through. So a negative aerated pile is it's a technique that uses a fan to pull air through a static pile of compost, thereby capturing the gases and the heat that would otherwise be released into the atmosphere. So in this way, we pull the air through and release it into a soil bed, which we call the biofilter, where there are actively plants growing. So if you can do this in the right concentration, the gases and the heat are released directly into that soil bed and can greatly increase the productivity while reducing the heating demand in the greenhouse itself.
The basic idea is to use existing natural processes and natural communities to filter gases that are otherwise released into the air. A biofilter is essentially a body of soil that has a wealth of life in it. And so the bacteria, the communities that are living within that soil, it's a saturated soil, so it's moist and it's warm, and it's an area where an immense amount of microbial and bacterial activity is happening. So this biofilter, rich in life, is an area that uses an immense amount of resources in the form of nitrogen gas and CO2 and the existing compost that's there. And so we provide those resources, the gases, through the compost system. And so we're essentially feeding these communities with nitrogen gas, which they're filtering out and enriching the soil, sequestering it from the gas and bringing it into the soil. And the rest, the CO2, is filtered through the biofilter, where it's released at a level where the plants that are growing the biofilter can use it. And that can reduce greenhouse gas emissions. It can increase the soil productivity because it's sequestering resources, sequestering things that we normally add to the soil through the composting process. Part of the greenhouse industry in Vermont, especially that's focused on growing food, is dependent on some sort of fuel stock. And so if that's natural gas or it's heating oil or propane, then those are sources that are subject to a great degree in fluctuations. And it means that producing food is becoming an increasingly costly endeavor in Vermont in the winter. And so if you can take an existing feedstock and without a major modification of the handling procedure can deliver heat through that process, then we're giving farmers security in the cost of how much it takes to produce food throughout the year. We can provide the data, which is really the expensive part of the process, and show exactly what the results are, then we're delivering value. And the system itself is relatively inexpensive to build. The technology is relatively basic. It's something that you can buy most of this at Lowe's or at Home Depot, and it's something that can be done that gives you a buffer against fuel cost. So the equipment that we're using with this project is incredibly basic. It's a rough cut lumber, PVC piping. There are the fan itself and the temperature regulation is probably the most advanced equipment, and it's something that you can buy on Amazon. So the arrangement and the actual sizing of the system and the results that you get from it are the complicated part, because the testing and the monitoring for it, especially for the gases, is expensive, and it's detailed work, and it's something that is well outside the general practice of a farmer that would be implementing a system like this. So our hope with the Clean Energy Fund and with UVM is that we're sort of leveraging the resources we have here to do that initial groundwork and to record the data, to find the patterns, and to be able to deliver an open source, basically a layout or the plans to create a system like this, along with the proven data that says, for the system of this size with this type of feedstock, this is the end result. And that gives a farmer more assurance that they can put money into a system like what we're talking about. They can buy the PVC, they can buy the local lumber, and they can buy a fan, and they can have results that are at least within a margin of error of the results that we've found here at the Hort Farm. So the Clean Energy Fund is a student-initiated fund. It takes $10 a semester per student, and that money goes towards renewable energy projects on campus. It's ideas that are proposed by students or faculty for research, infrastructure, and education around renewable energy and alternative energy. So the Clean Energy Fund offered us a chance to not only involve new stakeholders, but also to take this project with its
fell in between the lines of traditional boundaries within the campus, both academically but also in terms of funding sources. So we weren't going to somebody directly for funding for an agricultural project, and we also weren't proposing something that was strictly a renewable energy project or a business project. So the Clean Energy Fund, because it's inherently a multidisciplinary fund, it's the clean arena of clean energy is something that spans multiple areas of focus in academics. We were able to find funding for something that fell in between those niches that are already existing.
So our work with the Clean Energy Fund really enabled us to sit at the table with faculty and professors, assistant deans, and people that we otherwise really wouldn't have access to, that are leaders in their field, that are doing these things every day, that are teaching and that are doing research. And it gave us access as sort of connectors and student researchers that otherwise really isn't possible. And it develops the personal relationships and the network across campus to put together a project like this, and hopefully one that will have a lasting impact. So for us, that was sort of our first introduction to project management and to how you put together a team, and also bringing together people like the green building coordinator here, Michelle Smith, who's been, she's the real project manager, but it gave us access to professionals and people that are doing this as their livelihood. It's been a manifestation of our major that we've been able to design. So I think the point of this project is that it's combining some fields of study that are related but not typically done in tandem. So bringing together plant soil science with the dairy program and with the sort of business side of things. How is this a viable plan for farmers in Vermont? And those elements are something that UVM excels at. In and of itself is a small project, but we're hoping that it's a project that can be a model for research, for education here at UVM, and for programs that combine some of our strengths into something that's greater.